When you're running 210 half-gallon cartons a minute, you really don't get a slow warning that something is wrong. You suddenly just have cartons all over the floor. I remember one day when I was working on a line and we were doing water testing, we had a down bottle jam in our knockout area. And by the time I hit the stop, there were already hundreds of half-gallon cartons scattered everywhere. There was water all over the floor. The filler was still trying to run because it had no idea of the jam. And I just remember taking a step back and looking at everything. Well, broken water filled cartons, water dripping off of the conveyors, just the scattered chaos of what had just happened with this jam. And I laughed. I mean, at this point, it was already done. There was really no going back. So it just was a moment of humor after so long of working on this crazy project. We just it happened and now we had this mess to clean up. When you hear this term high speed line, 210 cartons a minute doesn't really sound that crazy. I mean, there are production lines that are running thousands of bottles a minute. 210 just doesn't really sound that impressive. But I can assure you, when 210 cartons a minute start hitting the floor, it feels pretty high speed. Welcome to From the Bucket, where controls design meets reality. I'm your host, Keely Smith. In this podcast, we explore industrial control systems as they exist in the field, not just how they were designed in CAD or how they look on paper, but how they operated in a production environment, how operators and maintenance interfaced with them, and the fun and interesting stories that I've made throughout the years of being a controls engineer. So the project that we're going to talk about today was another early career project for me. This is one of those projects that it was kind of one of those like bread and butter lines for the company that I worked for, because it was one of those lines that we were really good at. So most of the carton fillers at that time were running about 70 cartons a minute per lane, and they had two lanes. So you had 140 cartons a minute coming out of it. So that's pretty manageable. I mean, you're producing over a carton a second, but it's manageable. This line, however, was an experimental filler. So what they were doing with this one was three lanes at 70 a minute, or 210 cartons a minute total. And that really changes everything. After the filler, we had a few sections of conveyor, a down carton knockout, a massive accumulator that could hold like 5 or 6 minutes of product, a barcode verification system, and a monster case packer capable of running 3 packs at insane speeds. But really, none of that was a problem. That was all pretty standard equipment that when the time came, it just worked. It required very minimal changes. Everything was just running the way that it was designed. The real problem was the triple lane merge. See, the problem with having three lanes coming off of a filler is that at some point you have to turn that 3 lanes into 1 lane. And with 2 lanes, it's relatively simple. The math is pretty simple. Basically, you're just shooting gaps, and it's pretty easy to keep those in sync to where you send a carton in between the gap of the first line. No problem, easy. But 3 lanes just changes that. So the mechanical design at the time was this massive, massive merge table. I mean, we're talking 50, 60 feet of merge table. And it was pretty simple. We needed to zipper merge the cartons. Because what would happen is if the cartons hit each other, they would have that possibility of rolling off of each other, and that could potentially cause issues downstream when we were looking at like barcode verification, or when we went to push the cartons into a case. Having the gable in the wrong orientation could be problematic. At that 210 carton a minute speed, those small errors start to compound in almost violent ways. So I did what young engineers do. I kind of fell back on what I knew, what I had learned in school. So I went directly to the math. I remember building this ridiculous spreadsheet. I was pulling all of the dimensions off of CAD. I was looking at the conveyor lengths, the speeds, the theoretical minimum gaps, so I knew what my minimum speeds were. I was looking at just this incredible amount of data and throwing it into this spreadsheet, all so that I could come up with the overall speeds that I needed to run each of the conveyors at to make the merge work, figuring out how to get the gaps that I needed to make this mathematically work. Because at this point, I'm looking at this as, this is a math equation. It has to be a math equation, right? Because if I have a set number of cartons coming in at a set time, then I should be able to come up with this mathematical equation that says, yeah, if you run this conveyor at this speed and this conveyor at this speed, you'll be able to shoot the gap and drop the cartons in every single time. So gapping logic is pretty simple. It's a very simple equation. If you, for example, have a 6-inch carton and you're running at 70 a minute, your minimum speed that you can run a conveyor at to actually be able to physically hold all of your product is 35 feet per minute. Now, there's some physical restrictions that you have with this. So, for example, you wouldn't actually run a conveyor coming out of a filler at 35 feet per minute, because the problem that you would run into there is if you had something jam or you had to stop a conveyor or something, you have no place for a product to go. So you would typically want to run that faster. So again, let's just keep the math easy and say if I run at 70 feet per minute, now I have my 6-inch carton with a 6-inch gap in between each one. So cool. Now I've got a 6-inch gap coming off of my filler for 3 lanes. So mathematically, right there, that tells you that I don't have enough physical space to put 3 lanes together, because I only have enough space for 2 lanes to go there. So that means that between the filler and the start of the merge, I have to gain a minimum of 6 more inches. So the gapping makes sense. If you want to increase your gap, you increase the speed across a transition. If you want to close up your gap, you just slow that transition down. So that part's really easy. It's just speed changes on conveyor from one section to another. Now, again, there are some physical restrictions to that. You can't go and take a 6-inch gap and create a 18-inch gap off of one conveyor transition. You're going to end up just knocking the carton over at that point. So there's physical limitations on how much gap you can actually create, but it's a pretty simple equation. So I just remember I sat there and I modeled everything. I got to that point where, lane 1 needs to run at this speed. Lane 2 it needs to be slightly offset. I need to try and get the phase so that it's just barely out of sync with each other. So I've got this gap, this carton goes here. Okay, now I've got lanes 1 and 2 set up. And all right, now lane 3, yep, I've pulled enough of a gap here. So theoretically, lane 3 should fit right in here. So I got to that point. It all worked on paper. Everything was mathematically correct. So I went back to my PLC and I started programming this. I got all my speeds in, I got all of these different parameters in, and I ran it. And it actually worked, at least for a little while. And then it didn't. And what was happening was it didn't actually catastrophically fail. It was almost a little worse. It was a very subtle failure. If you watched it, the first carton would be in the perfect spot, and then the next one would just be slightly different. It wasn't wrong, but it was just slightly different. And then you watched the next carton and the next carton, and you could just slowly see things changing. And it unfortunately wasn't changing in a way that was beneficial. It was changing in a way where you could almost see it. It was like watching that car crash before the car crash happens. You just saw what was happening ever so subtly, and you knew exactly what was going to happen at some point. Eventually, you watch this long enough, and there it is. There's that carton hitting the next carton, and it rolls. I remember this just kind of baffled me because I had spent so much time going through the math and uh, modeling this up the way that I thought that this was going to work, but it didn't. So I go back to the math. I go back to the model, and where did I miss the calculation? Because again, I'm in this mindset where this is just a math equation. This is something that if I figure out where my math was wrong, I can just fix it and I can make this thing perfect. At some point, I finally found it. There it was. It was a compounding error. So, one of the things that, uh, again, you learn later in your career is um, it's not perfect. Nothing is perfect. So, when you create these models, you're not really taking into consideration that this is an industrial environment, and some of the things that you end up doing there is you make some assumptions, and with those assumptions there's a amount of error to it. And unfortunately, when you're working with something that you need a pretty high degree of precision, that error has the tendency to start compounding. So, yeah, while that first carton looks perfect, that second carton has that compounding error to it. So, the second one, again, it's not going to look that bad because you've only propagated that error across one carton. But when you start looking at it in multiples, like 5, 10 cartons, now all of a sudden that slight error it's noticeable. It becomes something that it's not just a, oh, that sucks. It's actually a, oh, this is going to cause a problem. At this point, I am deep into this mathematics problem. So I had to double down. It's just a simple equation. So there has to be an answer. So all right, let's go back to it. Well, let's see. It looks like I didn't have friction loss. I didn't have some transfer delays in there. There's some speed decay that happens when you cross those transitions. So okay, get that into the equation. Run through all of the numbers again, and cool. Now I have some new speeds to run at. So okay, back to the PLC, program it, run it again, and it's better. So, all right, now we're starting to see progress. So, if for example the very first pass at this, we saw one in every 20 cartons hit each other. Now we're up to every 40. All right. Well, let's go back to the spreadsheet, figure this out, and let's make some more changes. So, I spent days tuning this thing. So we're up to every 50 cartons, every 100 cartons, every 200 cartons. So at this point, you'd think, well, hey, that sounds great, right? But remember, we're running at 210 cartons a minute. So even if I get it up to the point where I'm only seeing one error every 210 cartons, that's still a constant failure. That's still every minute we have a carton that is rolling. I remember one of the cool things about this project and this line in particular was the customer was paying us to be there for weeks. So I had nothing but time to just sit here and try and really tune this thing in. So, one of the things to kind of preface this with is there was nobody was really looking at this and saying, "Hey, this is bad. Like you need to get this fixed." Because at even at one failure a minute, even at one failure every 30 seconds, we really weren't causing any major problems downstream. But at this point, I'm into this. I'm looking at this and I'm saying, you know what? There has to be a way to make this perfect. Perfection it's got to be attainable because again, I'm still in this mindset where it's just a math problem. It is simply just a math problem. So it should be able to be perfect. I keep going and I get it to that point where we're running 3, 4, 5, sometimes even up to 10 minutes where this thing it's running exactly the way it should be. It's almost mesmerizing to watch at this point because it's really well tuned in, but it wasn't perfect. And I think there was a moment there where, I kind of finally hit that plateau where I realized that there was no way that I could get it really any better with the math because I was missing things. So the math wasn't wrong, and quite frankly, the math is pretty simple. The part that I got wrong was this system truly wasn't pure math. There's there's variables in there that are almost impossible to actually quantify in that math equation. You've got points where your rails start to get a little tacky, so you get your product that can have speed changes that happens on your rails. Uh, you have friction that can change mid shift. I mean, a lot of this stuff happens just by running a product down a line. Uh, Occasionally, you get operators, they make changes on the filler, they do different things on the filler that it affects directly what's happening downstream. Sometimes we've got an issue going on in the filler and we'll start to miss cartons or they'll shut a lane off on the filler. All of that stuff is not really stuff that you can put into a mathematical equation to come up with this perfect solution. You look past some of that stuff and you look at how the table itself was mechanically linked. So we had motors, we had quite a few motors on this merge, but there wasn't quite enough motors to give you that crazy fine tuning resolution. So there was pieces here that I wanted, I just didn't have. So, I started to look at this differently. I stopped trying to solve this with the model and I start physically looking at what I have in front of me. At this point, I had already designed some vision systems, and one of the pretty critical things that I had in the vision systems was the ability to track a product from the time it hit a photo eye to the time that it was perfectly in the center of the cameras to the time that it got to the reject. So I had this idea of how you could do product tracking for a vision system. So I thought to myself, well, what if I apply kind of the same concept to cartons? So what I came up with was, well, what if I start time stamping a carton? So lanes 1 and 2 weren't problems. I knew what those were. Those were really easy to put a a gap number two, and there wasn't really much tweaking that ever needed to happen with lines 1 and 2 outside of if I needed to make a bigger gap, I made some speed changes. But lines 1 and 2 were simple. So what if I took the a time offset from lines 2 to 3, and I looked at what that timestamp is. So if I have a carton that is leaving line 2, because line 2 always got there first, and I measured the time that it took for the line 3 carton to hit a photo eye, and then I would watch it and I'd see, all right, so if I've got a 1 second delay between these two cartons, where does the line 3 carton actually end up landing? And I started to notice something interesting. It almost looked like a sine wave. So you would see where uh, it would gradually tighten, and then it would loosen, and then it would tighten again, and it would just kind of keep going through this cycle. So now I kind of have all this data figured out for, if this is the time, then I know it's going to hit perfectly. If this is the time, I know that it's going to be kind of in the wrong place. So, all right, what if on top of the math, because at this point, right, the math is still good. The math is what got us to this 99%, but I needed something a little bit different here. So, what if on top of the math, I start making a little bit of modulation in the line 3 speeds? So when I saw the drifts beginning, I could make a very subtle speed change and see if that would help. So back to the PLC we go. I add this code in there, and at this point it's really simple feedback code, and I run it, and it runs really well. Like it's kind of cool to see because the changes were so subtle that to the naked eye you didn't really know that anything special was happening, but I knew because I was watching it and I could see that, hey, this code was it was actually working, and it was almost perfect at this point. And then things started to happen. So uh, when I was talking about like filler changes being made, or uh, you're missing a carton. So the worst thing that could happen is you had a carton on line 2, which is the one that I was starting the timer with, and you were missing a carton on line 3. Now all of a sudden I have a huge time delay, and if you let your feedback loop overcorrect for that, it's pretty crazy violent reactions, because now all of a sudden my really simple feedback loop says, wait a second, you're way out of adjustment. So it tries to speed that conveyor up to crazy high speeds. So, okay, back to the PLC. Now we got to add some limits to things. We need to cap the adjustments. We've got to smooth the changes that it's allowed to make. So after a few more days of tuning, it's beautiful. The cartons still touched each other occasionally, but they weren't ever hitting that critical spot where they rotated. Every 10, 20 minutes, you might see one nudge another one, and it looks like it was gonna maybe do something, but it didn't, because there was just enough of that adjustment happening to where I could pull that carton off of it without rolling it. So at this point in my career, I'm looking at this and I am just absolutely feeling like $1,000,000. Like I got this thing to work. It's beautiful. Like there's no major issues happening anymore. And I I think the funny part to me, and I honestly don't remember at the time, but I don't really think that anybody really truly cared about like how perfect this merge was running. I mean, for me, this merge was like this was the thing. This was it mattered so deeply to me because it was just like this really really cool math problem slash just industrial problem that I had solved. So for me, this was like a huge huge thing. For production, I mean, they really didn't care. They didn't care when we were hitting cartons every 30 seconds. Uh, it ran for them. I remember the president of the company that I was working for. He came out, he watched it run, and I got the hey, great work, pat on the back. But he probably could have come out weeks before this, saw it run, and I would have gotten the same hey, great work, pat on the back. Nobody nobody saw like the weeks that I spent modeling this. No one saw the spreadsheets. No one saw all these notes that I had made of trying to get this data of well, this one was here and this timing was here and this nobody saw that. They just saw the cartons moving forward and the system running well and that was enough for them. But for me, this was such a huge growth moment. Like it's it was something that I hadn't really done yet. Uh, so beyond the fact that this was a huge, pretty complex line, this was where I kind of learned like, yeah, you design with the math, but you kind of have to stabilize things based off of how they physically work. Industrial systems are not perfect systems. So, sure, while the math got me 99% there, reality is the one that really dictated the success or failure of this because you can model things up as much as you want to on your computer and mathematically and all these things, but it doesn't really matter if the math says everything should work, but what's actually physically out there in the field doesn't. I think looking back at the time that I spent chasing this perfection on this line, I don't regret it. I think that, that struggle taught me that things are not exactly what they look like when they go from a design standpoint to a field standpoint. The struggle of getting to that point where that merge was working so well taught me way more than if I had just dropped the math into the PLC from the very beginning and it just worked. It really forced me to look at systems through just a totally different lens. It's where you learned that like engineering isn't just the modeling. It's not just how things work in the CAD, how it works on paper. It's it's the observation. It's the actual physical limits. It's knowing when you're good enough because uh, I guess one of the things now being later in my career that I understand is you'll never get a system to be perfect. There's a there's an actual metric that you can hit which is stable, but y- again, you'll never hit that perfection. And I think that this line was really the first time that I truly understand that. Like this was like crazy to me because you know y- everything going everything in school is perfection, right? Like every problem ends up having a perfect solution, and if you didn't get that perfect solution, well then it's wrong. So this is where like you really had to take a step back and look at it and say, well, the engineering by math is, that's how you get started. Actually looking at the physical system of how it was designed and everything, that's just the starting point. That's not the ending point. Engineering by how the line is actually running and how things actually physically work, that's the magic. This is From the Bucket, where controls design meets reality. Until next time.